Have you ever wondered how your computer just knows how much memory to use? Especially when a program has no idea how much it's going to need. Well, it's not magic. It's this really clever process called dynamic storage allocation. Today, we're going to break down how that brilliant and, yeah, sometimes messy, juggling act actually works. All right, so first up, to really get why the new way is so great, we have to understand the old problem. We're going to start by looking at the old school, really rigid way of handling memory and why it created a huge headache that somebody had to solve. And here it is, the fundamental difference in a nutshell. With static allocation, everything is locked in ahead of time. The program basically tells the computer, hey, I need exactly this much space before it even starts. But dynamic allocation? That's all about being flexible. It grabs memory as it goes while the program is running. Let's think of it this way. It's kind of like you're managing a hotel. The static way is like booking 100 rooms for a big conference months ahead of time. Now, if only 50 people show up, you've wasted a ton of money on empty rooms. But what if 150 people show up? Whoops, you're out of luck. That's the exact problem with static allocation. And that really gets to the heart of the issue, right? In the real world, programs are constantly dealing with unpredictable amounts of data. Static allocation just isn't cut out for that. You either waste a bunch of space by guessing too high, or your program just crashes because you guessed too low. It's just not flexible at all. So, what's the fix? Well, this is where the hero of our story comes in, dynamic memory allocation. It is a much, much smarter way to give a program the exact memory it needs, right at the moment it asks for it. Okay, let's look at the official definition. The key phrase here, the one you really need to remember, is during the program's runtime. This isn't about planning months in advance. It's about reacting in the moment. The program is running, it realizes it needs more space, and it just asks for it. Simple as that. And the advantages here are huge. You're using memory way more efficiently, no more empty hotel rooms, you can handle all that unpredictable data we talked about, and you can build these really cool, flexible data structures like linked lists that can grow and shrink whenever they need to. Honestly, it's a total game changer for programming. Okay, so this all sounds fantastic, but how does the computer actually do it? How does it manage this whole on-demand system without getting completely lost? Let's pop the hood and take a look. So, to the part of your computer managing all this, memory just looks like one long strip of blocks, kind of like a giant Lego board. Some of those blocks are already being used, they're allocated. And the others, they're free, just sitting there, waiting for a job. Now, the secret weapon for keeping all this organized is something called a free list, and it is exactly what it sounds like. It's a list of all the free blocks of memory. Think of it as the manager's little black book, keeping track of every single available spot. So, when a program says, hey, I need some memory, it kicks off this little process. First, the request comes in. The memory manager then scans its free list, looking for any block that's big enough. When it finds one, it carves out the piece it needs and gives it to the program. And then, and this is the really clever part, it takes the leftover bit of that block and puts it back on the free list as a brand new, smaller free block, so nothing gets wasted. But as you've probably guessed by now, this whole process of constantly splitting blocks and putting the leftovers back, well, it creates a pretty tricky side effect. See, in computing, nothing is ever quite that simple. So let's dig into that. What's the catch? What is the hidden price we pay for this amazing ability to get memory whenever we want? The cost is something called fragmentation, and it comes in two main flavors. External fragmentation is when you have tons of little free spots, but they're scattered all over the place, in between other data. So even if you have enough total free space, there's no single chunk big enough to be useful. It's why your phone might feel slow even if it says it has space. Then you've got internal fragmentation. This happens when the system gives a program a block that's just a little bit bigger than what it asked for, and that tiny bit of leftover space inside the block goes to waste. And this brings us right to the core trade-off, the constant balancing act that's at the very heart of how all this memory management works. This quote from the source material really just nails it. It's saying that sometimes it's actually smarter to accept a little bit of predictable waste inside a block, that's internal fragmentation, if it makes the whole system simpler and helps you avoid all those chaotic, useless little gaps that you get from external fragmentation. So the takeaway here is pretty clear. Dynamic allocation is an absolutely essential tool. It gives our programs the flexibility they need to work in the modern world, but it's not free. that flexibility comes at a price: the complexity of managing that free list and the constant fight against wasted space from fragmentation. And that really leaves us with a final thought to chew on. As our programs handle more and more data, we're talking AI, huge data sets, you name it, the challenge of managing memory efficiently is only getting more critical. The techniques we've talked about are the foundation, for sure, but the search for even faster, smarter, and less wasteful ways to do it, that's a constant frontier in computer science. You have to wonder, what's the next big breakthrough going to look like?